Right.
Yeah, it's fine. Okay. So, well, first of all, thank you very much for the invitation. I'm very glad to present this idea and to introduce computational social choice. So, as you will see, I am not directly an expert in collaborative systems and so on, but in the second part of my talk, I'll try to give you some hints, some insight, some recent work that I've found quite exciting. So this is also a way to open the discussion. So this will be very simply divided in two parts. In the first part, I will introduce the computational social choice area. So it's been very active in the recent years in AI. And there are, I believe, plenty of results which could be relevant for the Ensemble consortium. And then, as I said, the second part is going to be about some potential opportunities for collaboration. So I said large scale. I don't know if you would agree with that, but we can discuss about that later on. Okay, so let me start with computational social choice. So what is computational social choice? I will start with a quite dry slide to start with. So two foundational results in voting. So social choice is basically this theory of how you can aggregate preferences of different people, individuals over different options into a collective outcome. Okay, and you want to do that in a principled manner. So you would like to get properties, guarantees as to what the outcome will look like. So two very famous results from the 50s. The first one is the impossibility theorem of arrows. So what does it mean, impossibility theorem? It means that if you want your voting rule, so the voting rule would be something which will try to pick a single winner. If you have different people expressing preferences over different candidates, you would like to, so you know many of them, we use them for politics to start with, and in different contexts, of course. So you would like your rule to satisfy different properties, and the arrow theorem says something like, if you want to satisfy unanimity, independence of irrelevant alternatives, and non-dictatorial, then you cannot do the three of them together. Okay, so in other words, if you have unanimity and independence, it has to be dictatorial. And the Gibbard-Satterthwaite theorem is a bit different. It says that if your rule is surjective, strategic proof, then it has to be dictatorial. Okay, so at this point, I guess you don't really understand what I just said. I will give you a bit of background on these different properties. Okay, so I mentioned dictatorial. So what does it mean? Dictatorial means that a single voter can decide on the outcome. Okay, so you would decide the outcome just by looking at a single guy. Unanimity means that if everyone really agrees on the fact that A should be better than B, then overall the collective preference should say, okay, A is indeed better than B. Independence of irrelevant alternatives means that the preferences that you have regarding A over B should only depend on the relative preferences of A over B expressed by the voters, and not on some, I don't know, third option or different option. Okay. Subjective, that I mentioned also before, means that any candidate has a chance to win. So there is a possibility, there is what we call a profile, so a set of votes such that this candidate would win. Otherwise, this is someone which is excluded a priori from the procedure, and this is not something that we want, of course. And strategy proof means that no voter has an incentive to misrepresent a preference of the other candidates, meaning that if I was to change a little bit the way I express my preference, for instance, if I have my ranking is A over B over C, But if I realize that maybe it's better that I put B first, that's a way to strategize, and that's a way to misrepresent my preferences. Okay, so strategy proof means that the rule is not sensitive to that. And there are plenty of other properties. I'll just give you one of them, which is independence of clone, because I will talk a little bit about it later on. And it means that the presence of a candidate which is really quite similar to an existing one should not affect the outcome. Okay, so sometimes you can see this happening in politics, that there is a party created somehow to get some votes from another party because it's quite close. I mean, in principle, when you look at their program. Okay, so when you look now back to the slides, I guess it's a bit more clear what it means. So basically, some people would interpret that as saying, okay, so we cannot do much, but there are, of course, many, many ways that you can circumvent this different impossibility theorem. You can relax, you can some of the properties. You can actually realize that when you look at certain domains, then this would not apply, and so on and so on. So this is not the end of the story, of course. So this is classic social choice, which actually started way before, and you can get back to Condorcet and Borda and their studies of the voting systems and so on, and even before that. I'll say a bit more about that. But so the computational part came, of course, much more recently, and it's much also larger than just voting over a single option. You can think of voting also on a committee, so when you have to elect K candidates, or you can think of trying to aggregate different rankings into a single ranking. That's also something which is quite common. But social choice can also be concerned with different types of outcomes. For instance, the way you make matchings, so stable matchings, which is quite well known as well, coalition formation, fair division, which is also a very, very active topic in that field, either with divisible or indivisible good. And one of the key questions here is to really define what it means to be fair. And I also wanted to mention participatory budgeting, which is recently, which has seen quite a nice progress with a new procedure being proposed and so on. So there is a handbook on computational social choice that I recommend if you are interested in that topic. So what do people study in this field? So typically they can study the complexity of this collective decision procedure in the algorithmic sense, trying to see whether, for instance, a voting rule is simple to compute or not. And also, for instance, I mentioned before this idea of strategy and misrepresenting preferences. And these are some tasks which sometimes are difficult to do in the complexity theory sense. So this was seen as a way to, as protection in a sense, because, okay, if you can strategize, but if it's so difficult to compute what is actually the good way to strategize, maybe people will not do that in practice. So that's something which is interesting. Also, there are questions about the communication requirements of the different procedure. So how many information you have to convey to compute all these voting rules, for instance. The field has proposed new axioms, for instance, in the context of committee voting. I will mention a couple of them just after that, and also to design a new collective decision procedure. So there's a whole range of studies. This is not exhaustive, of course, but just to give you an idea of what's happening in the field. So let me talk a little bit more about voting. So maybe you have an intuitive idea, at least as someone who usually casts a ballot for political election. So one of the first key questions that you have to ask is what kind of preference you can assume. Okay, it can be a single candidate. So for instance, if you have to decide on the name of your project, you can say, okay, I want to vote for Ensemble. Okay, or you can actually approve different candidates. So, okay, you can have a ballot where you can say for each of the candidates whether you approve or not that candidate. So you say, okay, Ensemble is fine, Makoga, which is make collaboration great again, you don't want to approve for some reasons, and Team Up, okay, you also think that it's cool, so you approve as well. So that's a way to express. You can also express a ranking over the candidates. For instance, your favorite, your top option is Ensemble, then it's Makoga and Team Up. Or you could give a score to the different candidates. You could say, okay, I have 100 points that I have to spread, and I will say that Ensemble gets 42 points, and so on. So these are different ways to express preferences. Of course, you can already see that they have different cognitive and communication requirements. Okay, so for some of them, you just give a name. For the other ones, you would have to rank the different options. And if you have many options, that can be quite cognitively difficult. So sometimes you cannot do that completely. And so in practice, you would have to handle partially specified preferences, meaning that you only have, for instance, the top 3 candidates in your ranking, or that you just expressed some pairwise comparisons between options and things like that. So that's a very, very important issue as well, that you have to be able to handle partially specified preferences. So once you have the preferences, you have to compute a winner, and there are many different ways to do that. I guess you know that, but just to give you an example, so suppose that you have 6 people who voted for this ranking, so Makoga first, and then Ensemble and Team Up, and 5 voters with this Team Up, Ensemble, Makoga, and so on. So if you take the plurality voting, which is just plurality is just giving one name, so you would just look at the top option for each one of them. So you would get, so why is it 9? It's not 9, but it's 6 points, of course, and the plurality is the winner. If you look at Borda, so Borda is a way to compute a score where you would give 2 points to the first option and then 1 point to the second and 0 to the last one. If you compute that, then Ensemble would win. Okay, you would get 6 points here, 1 point 6 times, okay, and then same here, and twice this 4 voter here, so it's 19 points here, and this is the winner. And if you take a different perspective, which actually was the one proposed by Condorcet, if you try to look at the different pairwise comparisons between the options, you can draw what we call a majority graph here, where you look at the pairwise comparisons. So for instance, Ensemble has a majority of 2 when compared to Makoga, because if you look at actually the way Ensemble is compared to Makoga, you see that Makoga wins 6 times here, but there are 9 votes where Ensemble is above Makoga, giving you that should be a 3, I guess, majority. But you have a majority graph like that. And here it's very nice because in this majority graph, you have what is called a Condorcet winner, which is a candidate, an option, which wins over all the other ones. Okay, so this is an example taken from Sari. It's quite nice because you can see that what you actually got with plurality is completely the opposite. And if you took the different options, it's the opposite compared to Borda and Condorcet. So in general, there could be no Condorcet winner, and then you have to relax your notion. And this gives you different voting rule. And one of them is Copland, for instance, where you just count the number of wins in such a majority graph. There are also the Simpson rules and so on, the Schulz rules, and all of them are Condorcet consistent in the sense that if there is a Condorcet winner, they would elect a Condorcet winner, but if there is not, they rely on some principle to still give you a winner. Okay, let me now talk about a slightly different setting where instead of choosing one candidate, you have to choose K candidates. And in that case, you see that, for instance, here, I would have to choose 3 keywords for my project. So there are different proposals and there are different people who voted, approval voting for the different proposals. Okay, so for instance, this guy, agent 1 here, voted for AI and dialogue. Okay, and second one gave the same vote, and the third one voted for AI and bird, and so on and so on. So if you take the sum here, it gives you these approval scores. So a key question here is, what does it mean to be fair to the voters? And here, a notion that can be used is that of a cohesive group, which is a group which is somehow similar in the sense that if you have L times a quota, and the quota is given by the number of voters divided by the size of the committee, who approve L candidates in common, then you say that it's a L cohesive group. So for instance, here you have 9 voters. Okay, so the size of the committee is 3. The quota is then 3. Okay, and so the group, if you take 1, 2, 4, 7, 8, and 9, this is a 2 cohesive group because it has size 6, so that's twice the size of the committee. And indeed, they approve A and D in common, A being AI and D being dialogue. Okay, so this is a notion. And now, in terms of fairness, you could say that, okay, every member, if they belong to one cohesive group, they should approve some member of the committee. Okay, so suppose that the committee winning would be ABD if you just pick the one with the most approval votes here. And so in that case, you see that agent 6 is not represented, but it's not, so they could complain, but it's not really justified because she does not belong to a cohesive group. Okay, she's a bit on her own, voting for just cool, and so there is no proper justification of giving her a fair representation in the final committee. If instead 7 voted for that, then in that case 6 would belong to a cohesive group where you have 3 agents here voting at least for one candidate in common. And so C should be in the committee. So you could have in the committee A, C, D. And in that case, the complaint of 6 would be justified because of belonging to this cohesive group. Okay, so these are some notions which have been developed in approval-based committee voting. Of course, there are then different rules to come up with this committee and so on. I cannot get into the details here. But this strong representation is not always achievable. Just to show you an example here, if you require really everyone to be represented, you could have a situation like that, where because of these 3 people here, you would have to put A in the committee. Because of those 3, you would have to put B, and the same for C and D. So in principle, you would have to put A, B, C, D, and if the committee is just of size 3, you cannot do that. So that's why researcher looked at relaxation of this notion, and instead of requiring that all the member in the cohesive group should see at least should get one approval in the committee, then the requirement is that at least one member of the cohesive group should approve L members for L cohesive group in the committee. So this is basically a relaxation, and we know that there are rules which can guarantee this relaxation. So just to give you some insights, and also I'll get back to this notion right after. Okay, so now I would like to tell you a bit about some recent work that I came across and I found quite stimulating, and I think that they can be relevant in the context of Ensemble. So just a word of caution before I get any further. So at this point, I will assume what I call large-scale collaborative system with some predefined purpose and potentially a high level of dynamicity where so users can enter and leave the system. And so I guess this is also related to the discussion which started before, related to Dominic's presentation. Some examples would be Wikipedia, OpenStreetMap, and deliberation platforms, what is nowadays called collective dialogue systems. And just a disclaimer, so I've been working on deliberation platform recently, but for many others, I don't really have expert knowledge of their detailed mechanism. So sometimes I just remain quite abstract, and I'm really looking forward to your feedback on some of the detailed platform. So my objective is really to provide some examples and to foster discussions. So first of all, when you talk about voting in this type of systems, it's seen with reluctance because there is this idea that voting is a bit orthogonal to deliberation and consensus. So when you look at Wikipedia and the way they talk about how to use polling, for instance, this is really very careful in the sense so you can read consensus is an inherent part of the wiki process. When conflict arise, you should use discussion, debate, collaboration. So polling is not formally forbidden, but you should really be really careful. So this is taken from the policy of Wikipedia. Another thing that really happens on these platforms is that even if you have people who expressed preferences, typically this will be very sparse. So there are potentially many different options. So for instance, if you take deliberation platforms, you can have plenty of statements which have been expressed, and you cannot assume that everyone will vote on any of them. And also some statements can appear later on in the process, and you cannot really get in touch with some people who maybe left the platform in the meantime, and so on. Just as an example, on the platform which we look at with some PhD students and colleagues, it's deliberation platform, argumentation platform, which is called Chialo. It's well structured, so you build argumentation graphs together in a collaborative way, and you see the distribution of the votes. So actually half of the arguments and claims do not get actually any vote, and until 70% you just get one vote, and you see that some claims get many votes, but it's really quite sparse overall. So this is taken from a work of a PhD student who looks at this platform. But there are still many opportunities. So I'm sorry, this is maybe a bit too small to read, but I just wanted to give you this this reference. So it's a paper with many authors, and it's called AI and the Future of digital public square. So you have political scientists and so on trying to discuss the new generation of deliberation platform, basically what they call uh, collective dialogue systems. And they identify different ways that you can use AI systems. And for some of them, social choice is really involved. And I'll talk a bit about that. So you can see that the way you recruit participants, the way you educate them in the participation, summarizing, sense making, um, visualizing the opinions of the different people, and of course, delivering the outcome. And finally, I wanted also to emphasize this generative social choice paradigm, which appeared recently and which is a way to integrate the ability of large language model to generate new options during the process with the principle-based approach of social choice. So the idea is to reach collective answers to open-ended questions in a scalable and principled way. So that's quite new, and I will mention work which basically is quite related to this area. So the idea is that LLMs can provide new options during the process and also can be used to extrapolate preferences of individuals. So a couple of works that I found quite interesting. So recently, actually, a colleague of ours, Nimrod Talman, visited, and he gave a seminar on collaborative writing. So I guess also related to Dominic's talk, and it tried to introduce different way that social choice could be used as a principal way to organize collaborative writing. So typically in these systems, this is a setting where you have iterative voting, because you can vote on different paragraphs, for instance, that you would like to include in the final document, but you can also retract your vote in some way. So this is iterative in this sense. And this raises the question as to how you can guarantee that you will converge to some state which will be stable. Okay, if people can really keep um, changing their vote all the time and so on, then how do you decide that you will reach a stable state? So they introduced these smooth rules which will require, so it's basically a quota rule where the quota will change over the time, meaning that at the beginning you can actually change the decision quite easily, and as time goes by it becomes much more difficult. So the quota becomes higher, and it's more likely that you can reach stability that way. So I found this quite interesting as a way to vote, and it's an example where the voting rule is dynamic in that sense. Another recent work that I found really exciting is about comment sorting. So that's so the question here is how you present different comments to users on the platform, and how you can query voters to get the most relevant information if you want to fairly represent the diverse opinions at the end of the process. And the key idea here is that actually selecting a subset of comments based on the different agreements and disagreement of people is the same as electing a committee based on the approval vote. So what I presented just before can be used as is, as a principal way to select different comments. And in these recent AAA papers, some colleagues looked at different algorithms to then query the voters to look for the most relevant queries. And what they call adaptive algorithm will select the query based on previous vote. And using that, you can achieve good results in theory and practice. In theory, it means that you can achieve the justified representation guarantee that I mentioned before. So if you do that, you know that you will achieve some theoretically well-founded notion of representation. And in practice, they have some experiments with Reddit, if I remember correctly. And finally, and this is the final work that I will present here, I wanted to tell you about the Habermas machine that maybe you've heard of. The idea here is to find a consensus statement which will maximize the participants' approval. So it's used in deliberation platform as well. So for instance, to help with citizen assemblies and things like that. And the process goes like this. So you have individuals which will who will propose free text answers to open-ended question. And then some large language model will generate candidate consensus statements. Okay, so a single statement trying to give a consensual view of the different answers which have been given. Then the participants' preferences over the statements are inferred from some feedback that you would have obtained before at a preliminary stage. And then you will rank, you will aggregate the different rankings using the Schulz voting rule that I don't have time to present, I'm sorry. You pick the 4 top ones, and then you will ask participants to rank themselves the 4 selected statements, and again use the Schulz voting rule. Then the participants, so in the end you get a single candidate consensus statement. And then in the end, you ask participants to comment and critique the winning statement, and you loop and you iterate. So they have results. So this is a science paper called AI Can Help Humans Find Common Ground in Democratic Deliberation. And they show that actually with more than 5,000 participants in the UK, on some debates, they obtained more approval for the AI-generated group statements as compared to the human mediator. So if you want to look at the details, I give you the reference here. Okay, and just to conclude, so just to say that I believe that computational social choice offers quite a variety of results that can be used in collective decisions and collaboration settings. So collaborative platforms are very likely to benefit from some of these insights. I think they also raise some exciting new questions, so that's very nice. And of course, you always have to keep in mind, but this is also related to Dominic's talk, that the objective is to enhance human collaboration, and so the consequence of this AI-supported system should be carefully investigated. Just to say that there are also other topics that I did not have time to mention here, because otherwise I would have taken 3 hours, and I'm already quite late on the timing. But just to give you the final thoughts about this, coalition formation, I believe, is of course very relevant, and fair division, perhaps it's less obvious, but it's also the topic which is quite close to my heart because I work on that. So if you have any good ideas of how to use fair division in the context of your work, I would be very happy to discuss that with you. Okay, sorry about the timing.
Thank you, Nicolas. Well, you are actually, yeah, some minutes late, but let's say it's fair enough.
Thanks.
Okay, so first, does anybody have some clarification questions before we start a broader discussion?
Yes, I do.
Go ahead.
I have two questions. First, thank you for the talk. When you introduced Arrow and Gibbard-Satterthwaite theorems, I directly thought about Condorcet method, and maybe you answered this question in your talk, and in this case, I'm sorry, but doesn't the Condorcet method and Borda method disprove those two theorems? This is my first question. And the second is, I already knew the Condorcet method, and I intuitively inferred that for me it's better than a classical majority method. But what are the arguments for the Borda method and the Condorcet method? Because certainly there are arguments for one against the other, but I just see the arguments of the absence of a Condorcet winner. But apart from that argument, what are the arguments for and against each of those two methods?
Okay, so that's a good question. So no, it does not disprove. So first of all, the theorem. So for instance, if you look at scoring method, they would not satisfy the independence of irrelevant alternatives because the way you rank your options, it will make a difference whether you have plenty of options in the between or not, for instance, or things like that. So for each of the methods, you would have some properties which is not guaranteed. So this is a very long debate and still ongoing debate. There are some arguments of simplicity. For instance, for Borda, it's true that it's a method which is quite easy to to explain, and also that can be used quite broadly. Of course, the main problem with Condorcet method is that when the Condorcet winner does not exist, then you have to rely on some relaxation principle, which can be a bit more difficult to explain. There are some, so it really depends on, in the context that you are considering, what are the key properties that you would like to see satisfied. I guess so. For instance, it is known that some notion of reinforcement. So for instance, if you take a subpopulation and this subpopulation votes and elects A, and a second subpopulation votes and elects A as well, then if you take the whole population altogether, you would still want to elect A. Okay, so this is called a reinforcement. And we know that some rules will or will not satisfy, depending, for instance, whether it's a scoring rule or not. So again, I guess it really depends on the key properties that you would like to see satisfied. There are people strongly defending some of the methods. So for instance, if you take the Habermas machine that I mentioned in the end, one of the key reasons, or I guess the key justification that they give for using the Schulz method, which is a bit long to explain, but it's a Condorcet method basically, is that it's one of the few rules which is independent of the clone. So it means that if you have similar candidates, so in that case similar statements, you would not want that to affect the result. Okay, and for them it was important to have that property, so they justify using Schulz methods like this. Okay. Yeah, so it really depends. All the methods have their drawbacks as well. Some of them are actually difficult to compute. Some of them are more difficult than others to understand, to manipulate, and so on. And so, yeah, I have no definitive answers, so it really depends on the context. And sometimes it's difficult to, well, just consider the political situation. If you want to change the way people vote, the way the system that we use, it's quite difficult, and because we know that we would lose. So we use majorité à deux tours, plurality with a runoff in English, and it is known that it's not a very good method. Actually, it does not satisfy many of the properties. So, for instance, it does not satisfy monotony in the sense that if you improve your vote for the winner, then it can make the winner worse off in some sense, which is quite strange as a behavior. So, but it's very difficult to I think in many contexts the simplicity of the rule and the simplicity also of the amount of information that you have to provide